and then just take it with exam, okay? So sorry for now recording this part. So let me just quickly show the guys who's watching the YouTube later. This is what we've done. We have carried out previous moment coefficient factors, bring the number here, just take the loading and calculate them, get the numbers. And I want to focus on the units. It has to be kept foot per foot, okay? The unit here is very important, important unit, because you see this in the exam, okay? Okay. Alrighty, any questions, guys? Are we good on here? Okay, well, silent again. All right, so let's assume we're okay. And of course, stay behind if you have any questions, okay? Stay behind if you have any questions, okay? So let me stop sharing and then go to our next lecture, which is on the serviceability, So where are we here? Okay, so lecture 19, serviceability, lecture 19, serviceability, okay. All right, so let's review, right? Before we start, let's review. So this is lecture 19, serviceability, right? But before we do this, let's have a short review. Right? So what we have talked about so far, I keep mumbling in the past weeks, talking about equations, slabs, strengths, all that. So what we have talked about so far, right? That's a big what, right? So what we have talked about so far. So I'm gonna name some names and start to see if we remember anything. So who's on my list? Michael, Mr. McKernan,
Yeah, yep.
how are you, man?
We talked about like bar spacing,
Okay, bar spacing. All right.
shear,
Shear, good.
and design of beam members.
Design of beam members, good. What else?
Uh, like
What we talked about?
uh,
Minimum,
yeah, like minimum spacings of bars,
sure.
minimum
These,
areas, all that kind of stuff.
right? These are here, right? Right. So what we talked about today in last lecture,
Last lecture we were talking about
one way slab, right?
one way slabs.
Right, right. And specific for one way slab, we talk about moment, but no shear, right?
Yeah.
Okay, thanks. That's all we talked about. Great, that's all we talk about, yes. So we talk about how we analyze the bending, and this is moment here, of a beam member, okay? We talk about shear, how to design spacings, so shear reinforcement spacings, okay? And in the moment for the beam members, we talk about two things, right? We talk about two things, singly reinforced and doubly reinforced. Okay, and if you really want to talk about it, we also mentioned there are two separate things, and we talk about known section design. For known section, you're designing the reinforcement, and the other is unknown section. You have to determine the section. This is a long, long time ago in a galaxy far, far away, right? So long ago, right? So that is what we talk about. That is what we talk about. Okay, and you see that all these all these, right? These are for beams and slabs, but all these are what? These are for designing for strengths, okay? Or load bearing capacities, load bearing capacities, right? So all this can be summarized in one equation, right? So that is either mu or vu, right? It has to be bigger or smaller, sorry, the other way around, smaller or equal than phi mm or phi vn, right? So that's what we talk about. This is design for strengths. And going all the way back to the beginning of class, we mentioned that design has to satisfy two criteria. Design, okay, design satisfies two criterions, Okay, so what are the two criteria? One is what we talk about, the strengths. Okay, strengths, and this is Mn, Vn, and later we'll talk about column, Pn. Okay, and then the other big criterion is the serviceability. Serviceability. Okay, serviceability oriented design. Okay, and this means we have to consider deflection, okay, which is deformation of the beam, cracking, how many cracks are allowed in a beam, whether we allow cracking or the cracking forces, and bonding. Bonding means what? Bonding means how much length that you have to provide it for the bar to be sitting inside the concrete to create proper transfer of stress. Proper transfer of stress. Okay. Now, today, mainly we're going to focus on deflection. Okay. This is what we're going to talk about today. Okay. How much beam can deflect? Okay. So talking about deflection, we need to know the equation for deflection. Okay. Equation for deflection. So I'm gonna call my next victim, see if we remember from structure analysis. Ben Wood. Mr. Wood, are you there?
Yeah,
Hey, how are you doing, buddy?
not too bad.
Okay, quickly, thank you. And let's recall if we want to calculate deflection of a thing, right? So I have a simply supported beam, right? And then I have some loading on top. What do I need to know to calculate deflection in terms of section properties?
The modulus of elasticity.
Exactly, that's E, right? And then I had to know the section, right? So cut the cross section, for example, this is square. What do I need to know about this section?
The moment of inertia.
Exactly, moment of inertia. Thank you, that's critical, right? So essentially all we need to do is Young's modulus and moment inertia. For Young's modulus, there are two parts. There are two parts, right? We have the concrete, we have the steel. Okay, and for moment inertia, right, it has this section right here, but remember our section allow cracking. Our section allow cracking because remember in the Whitney stress block, there was assumption made. What assumption made? Made that there was some compressive zone here, and at the tension zone, we assume there's no contribution in terms of tensile strength from the concrete. That means we have to do a transformed moment of inertia, which we'll talk in details, right? It's not original moment inertia anymore, it's transformed moment inertia for this. Okay, so that is what we're going to talk about, how we determine basically the moment of inertia of a concrete beams. Okay, so let's take a look at the learning objectives, right? What we need to learn for this, what we need to learn from this, okay? So learning objectives for this section, okay? First, we need to know how to determine the moment of inertia. Determine the moment of inertia for a cracked, for uncracked first, for a uncracked transform section. And I will explain what is this transform section, right? What is this transform section? Okay, and a crack but elastic. These are another new word for us. Crack, elastic transform section. They're different. They're different. Okay, they're different. All right, and though we have to know, next we have to know how to calculate the stresses, right, of uncracked transformed section and a cracked elastic section. Correct. Elastic transformed section. Now you see this a lot. You start to wonder, what does the transform mean, right? What do I need transform to or from, right? transform, what does it mean? So we explain, right? And then last but not least, we need you to be able to describe, the crack control, provision. Okay, control provision. Okay, with ACI 318. In essence, we need to know when we allow them to crack, how much we allow them to crack, or we don't allow them to crack at all. We don't allow them to crack at all. Okay, so these are learning objectives. So let's get to it, right? So first of all, I want you to have a concept of serviceability from the higher level. So there is a design limit state. Okay, and this we talk about in chapter 2. Okay, and design limit state divided by three categories. Okay, which three? There are ultimate, okay, and this is based on ultimate loads. That's what we've been talking about before, right? Oh, sorry, let me change the color a little bit. Based on, just say MU, VU, and for the column PU, we haven't talked about column, we will, okay, we will. And then serviceability, which is what we're gonna talk about today, serviceability, okay? And this is at the service load, so based on service load. Service load means it's not yet so much, it's gonna break your structure, but it's sustainable, right? Some loading you have to consider. And then last but not least is special loading. And in this special loading, we're talking about hazard load, means like seismic, earthquake loading, basically. Okay, and hazard, for example, tornadoes, wind, rain, snow, excessively, those are the special loading. Okay, so what we're going to focus is the serviceability based on service load. So based on service loads, there are two things we concern ourselves, right? One is we call it deflection. Okay, this is called deflections. How much it moves, how much it bends. And the other is crack, how wide the crack popped open, because we want our rebar to be safe. Okay, so these are the two criteria. And on top of these two, we're going to focus today on fact deflection. Okay, so mainly for beams. Okay, mainly for beams, because beam deflects. Okay, so how beam deflects? How does beam behave, right? How does beam bend, right? So recall what I did before. 3-stage, okay? 3-stage of flexure behavior. Now we briefly went through this long time ago, but don't worry, we're going to remind you. 3-stage of flexural behavior of a RC beam, reinforced concrete beams. Okay, what are 3 stages? So let me just draw the diagram, right? So say I have a y-axis, and this is in terms of moment applied to the beam. Okay, let me draw it quite big, and let me set a x-axis, and I call this to be curvature. Okay, in case we all forgot about curvature, remember, this is the region of section, and if I draw a strain diagram, this is epsilon Cu, this is epsilon S, right? And the curvature means this angle right here. So this curvature phi equal to 1 over, actually 1 over kappa, but okay, you probably don't have that concept yet. So you can just think of it as an angle, okay? Think of it as an angle of the curvature, okay? All right, so the idea is I want to see when I apply moment, how does this angle changes? Okay, so beginning of the stage, right? When I have my beam intact, okay, so this is not epsilon Cu, this is just concrete compressive strain C, and this is steel, but the bottom section of the concrete, right, still takes tension. It can take tension. So that means when I talk about the behavior of this beam, right, and this is still E I, where I equal to the moment inertia, that is 1/12 BH cube. 1/12 BH cube. Okay. But once I reach the cracking moment, remember? Once I reach the cracking moment, okay, all of a sudden my concrete start losing its tensile resistance. Only the steel start pick up the tensile resistance. Okay, and then I have a dip or slide in terms of curvature. My curvature increases suddenly. All right, and then I enter the second stage. So if I name this stage 1, linear stage, and then my second stage looks just like this, a little bit non-linear, but goes up. Okay, goes up. Okay, now in the second stage, my concrete has cracked. Okay, so here, if I say that this is uncracked, okay, but here's cracked. Okay, but when I see the concrete has cracked, my compressive strain of the concrete, concrete hasn't reached the maximum yet, and my stress strain relationship in the concrete remains elastic. That means in the second range, in the second stage, remember the material behavior of concrete? It looks like this. Okay, so when the second stage, before we hit the peak, this is where the second stage is at. Means the stress and strain relationship of the concrete still remains elastic, linearly elastic. So I can proceed further, but to the point that my bar, my steel reinforcement yielded. Okay, my steel reinforcement yielded. I entered to the last stage where I almost see a flat of moment capacity, Okay, and this stage is called stage 3. And this stage is called stage 3, and this is called ultimate strength. That means you cannot have higher strength than this anymore in terms of moment capacity. Let me just label a little bit longer. Okay. So these are the 3 stages. These are the 3 stages. Okay, so let's just name them, right? So stage 1, okay, we call it uncracked. Again, when I say uncracked, that means, right, that means my cross section remains. And when I calculate moment inertia, IG equal to 1/12 BH cubed, and this is B, and this is H. Okay, so when I calculate deflection, I use the whole moment of inertia. But, is that right? But there is a tiny element that I has ignored, which is the reinforcement AS. Okay, and I have to consider the AS into computing IG, and I will talk about it why. Okay, but right now you can say that, okay, the section is still intact. Now stage 2, okay, we call it cracked elastic. Okay, that means in stage 2, I have only maybe half of the section still take care of my compression, looks like this, and the other half just cracked. So my neutral axis is somewhere like this here, and I still have tension, still reinforcement in here, Just so you remember, and this is what we said, right? But instead of Whitney stress block, we have a linear distribution of stress because it hasn't yielded yet, right? And then we have a tension, right? So this compression and this is tension. Now, the reason why we need to consider it differently from previously is that in the previous, we only care about, if we say we're trying to find MU and design loading, this means we're right here, somewhere here. Okay, that's for MU, MN, and all that beautiful stuff, right? But when we talk about the deflection, we only care about here. Okay. Okay, so let me just call it here. So this is deflection. Okay, surface deflection. We only care about these two stages. We only care about these two stages. Okay, all right. So this two stages is, we call it daily operation stage. Meaning most of deflection, let me put a star mark here. So most of deflection in service comes from, comes from these two stages. Come from stage 1 and stage 2. Okay, so this is the key for calculating deflections. Hence, right? Hence, you know this. We need to know. Hence, we need to know. Need to know what? Need to know moment of inertia. Moment of inertia. Okay, for stage 1 and 2. We need to know moment of inertia for stage 1 and 2. Okay, 1 and 2. All right, so now you can see after this whole preparation, a long story, right? We're trying to tell you that we need to calculate the moment of inertia. Calculate moment of inertia. Okay, all right, so this is where we're going to start about the serviceability, right? That's just the concept. Okay, so circle back on the writing here, right? On the writing here, let me just put some emphasis here. So I keep talking about transformed, right? So you might be curious, what does transform mean, right? Why do we need transformation, right? After all, we're not in the mechanical department transformation, right? What we're talking about, right? What we're talking about here, let me show you, right? So why transformation? What is transformation? What are we transforming, right? And why? Okay, why? Why is that? Is because RC beam is a composite section, is a composite beam. What does composite mean? It means it has two materials, has two different materials, right? Has two different materials. And this is my drawing. And these two materials are concrete and steel, concrete and steel. Okay, concrete and steel. I have concrete here, and I have steel here. So why bother? Why bother? Just different materials, why bother? Bothers because the modulus is different. Concrete and steel are different. How much difference? How much difference, right? So for example, concrete EC is roughly equal to 57,000 square root F prime C. Okay, and but steel, for steel, right, ES could be, is a constant, right? It could be higher than 20,000 KSI. Okay, so how much difference we're talking about? See, if we name this, define N, big capital N, as a modular ratio, means ratio of modulus between these two materials, okay? And let's define it to be between steel and concrete. And you will find out for concrete strength F prime C, say 3 KSI, okay? This number is as high as 9.3, 9 times higher. Steel is 9 times stiffer than concrete. All right. For a higher strength of concrete, say 6 KSI, this number drops a little bit, but still has a number of 6.6. 6.6, almost 7 times higher. Okay, almost 7 times higher than concrete. Okay, so this means we are roughly having a 8 times of difference in terms of modulus. 8 times different in terms of modulus. So we cannot treat it as a one material, monomaterial section. We cannot treat it as a monomaterial section. So cannot treat RC section monolithically. Okay, so we have to treat it as a transformed section. We have to treat it as a transformed section. So transformation is needed. Transformation is needed. Now, question is, which transform to which, right? What transfer to what? So here in this class, we're going to transform steel to concrete. Okay, steel to concrete, and this is how. So for stage one, okay, that means uncracked. The concrete hasn't cracked yet. Okay, uncracked. And let's take a look at section. So the section looks like this. A big old rectangular block. I have a row of reinforcement at the bottom. Depth of it is D. Okay, height of it is H. Okay, and the width of it is B. Okay, so this is my section. This is my section. Okay, so how to transform it? How to transform it, right? First of all, let's take a look at the strain distribution, right? Strain distribution, so it's linear because it's uncracked. So I have a concrete strain here and steel strain right here. Okay, since it is linear, okay, since it is linear, okay, that at the end of the linear stage, I know for a fact that I have reached the tensile strength of concrete at the bottom fiber. Okay, tensile strength of concrete at the bottom fiber. So this stress at the bottom fiber has to be smaller or equal than Fr, modulus of rupture for concrete. Okay, and the top is just the compressive strength of concrete. Usually don't have to worry about it. Okay, so it is this criterion we have to check. We have to check if it is the case. Because if it's not, we cannot assume it's uncracked section and we cannot do the transformation. All right, so for the transformation, what we're gonna do is we're gonna treat the whole thing as a concrete section. Okay, all right, here's the trick part, okay? Be very, very vigilant, be very, very careful, okay? So of course, this shaded area, and then, you know, that's the regular old section, and this is B, and this is H, right? Everything just as we shown before. But now we have to add steel to it. How to add steel? Now we're going to draw a small tiny wings at the height of the steel. The height of the steel, okay, these are the same height in case you didn't see it, okay? And you have tiny wings like this, okay, stick out. Okay, and this is a transformed area of steel. Okay, this is transformed. And what is this area, right? What is this little wings here? So turns out all these add up together equal to n minus 1 AS. N minus 1 and the AS. Where they coming from, right? So now recall, we define N as kind of the ratio, stiffness ratio between concrete and steel. So if I want to have, if I have 1 inch square of steel, right, and that equal to N times of that much of concrete, okay? But this is just the steel, right? And I have these original area occupied by the bar, so I have to remove. So I have to remove its own area, and that's where it comes from. So essentially is we're going to use a solid blue block added by this little red wings, and this wings is at the same height as the reinforcement, but with an area of n minus 1 AS. Questions? Is it clear? Is it clear? Bryce? Hello, Bryce? You there? Did I lose you, Bryce? Hello, Bryce Kuiper? You there? Oh,
Hey, Bob.
hey, can you hear me?
This isn't Bryce. I have a different question.
Oh, okay, go ahead. First of all, what kind of question you have?
What could you show the typical N values for the concrete again? I missed those. Perfect. Thank you.
Okay. And in our calculation, we typically use a n equal to 8.
Okay.
Okay. All right. Well, Bryce is now here, or he's here, but microphone is not working. Let me find another victim then. See here. Justin. Mr. Heckman, are you there?
Bob.
Hey, how are you doing, man?
Good. How are you?
Good, good, not bad. So can you help us out on this? So if I have this little wings, right, and I have n minus 1 AS, what if I have compressive bars on the top? What should I do?
With that,
So I will still,
compressive zone would get bigger, but
right. So I can use the same approach, right? Essentially is I can draw the wings just like I did at the bottom, right? Question is, what would be the area here? Is it n minus 1 or n plus 1 or what? Or NAS?
it'd be N plus 1
Why?
because you're contributing to the modulus of concrete rather than taking away from it.
Well, it's n minus 1, okay? That's a trick question, yes. But I mean, the idea is that if I want you to think about it, right? There's a mind thought process. Essentially is you take the bar out first, you leave the empty holes, okay? So think of it, right? Once I take the bar out, I want you guys to think of it. Once I take the bars out, I just leave a empty holes like this. Okay. First thing I do is I fill it with concrete. Isn't it? So that's the minus and the AS coming from. Okay. But the total contribution of the steel is NAS, N times AS. Okay. Hence, I got N minus 1 AS.
Oh, I gotcha.
Right? Right. So I'm just using example because I'm pretty sure I went too fast and a lot of us didn't catch it. So there's a taking out process, okay? Taking out process. So it doesn't matter as long as it's this uncracked stage, as long as it's uncracked stage, either the bar is at the bottom or I don't know why this is coming out, either the bar is the bottom or the bar is at the top, you do the same process.
Cool. Thank you.
Yeah, sure. Thanks a lot. Okay. All right, guys, is it clear? Okay, now here's my quiz, quiz number 8, okay? Quiz number 8. All right, a quick one. So quiz number 8. Okay, quiz number 8 is that I have a section, okay? And I have a 12-inch of width, 12-inch of width, and 24-inch of height. Okay, and so F prime C is 4 KSI. Okay, and the modulus of steel, let's say 29,000 KSI. So first, question A, I want to find the modulus ratio. Okay, two-step, right? And then say I have 3 number 9 bars at the bottom. Okay, 3 number 9 bars at the bottom. Okay, I want you to find the total transformed area. Okay, total transform area. That means I want you to give me, this is the section right here with the bars. I want you to transform it into a section like this and with little wings. Okay, and I want you to add them up together. So A transform say equal to part 1, part 2. So 1 plus 2 equal to A transform. I want you to have the total area. Okay, that's quiz number 8. Okay, all right. Okay, I think this is a good point to stop. Again, you're welcome to stay behind. If you have any questions, let me stop recording.